Math 1343, week 10, video 6. The ANOVA table. Folks, that's a little bit better. Change locations. All right, so we've talked quite a bit in theory about analysis of variance and the fact that we're testing multiple population means to see if they're equal, as opposed to at least two of them being different. We've talked a little bit about analyzing pictures of sample data sets to determine whether or not there's cause to believe that population means might be equal or possibly different. We've talked about conditions under which the F distribution is appropriate for an ANOVA test. And we've talked a little bit about calculating variability. In fact, the three types of variability: variability within groups, variability between groups, and total variability. But what we haven't really done yet is get to the meat of the hypothesis test, which is comparing a test statistic to a critical value, if we're taking the critical value approach, or calculating a test statistic followed by a p-value to compare to the significance level if we're using the p-value approach. So, but either of those require calculating a test statistic, so now it's time to get down to it. How do we do this? Well, honestly, an ANOVA table is just a gigantic formula, but it's organized into a table so that you go step by step to get your final results. The end result is the test statistic that we're going to use for ANOVA, and it's used to test a null hypothesis that all population means are equal, opposed to an alternative hypothesis that at least two population means are different. So what does this ANOVA table look like? Well, it looks a little something like this. There we go. You have multiple columns and multiple rows. The rows are separated based on, there we go. The rows are separated based on whether you're talking about the groups, the errors, which is like measuring how far off each number is from its mean, and then the total. And then we have 5 or 4 columns, well, 5 columns, one of which is descriptive. The source of everything, column for degrees of freedom, column for some SS's. Now, these are the variabilities that we talked about before: SSG, SSE, and SST. And all of those have formulas, but for the sake of discussion, let's say that we've already calculated those values. Well, what happens next is we calculated a couple of things called MSG and MSE. MS stands for mean sum of squares, and then we calculated test statistic. The way an ANOVA table works is you typically fill it in from left to right. In the degrees of freedom column, we have 3 separate degrees of freedom, but we only really need 2 of them. We're going to need the degrees of freedom for groups and the degrees of freedom for errors. The degrees of freedom for groups is k minus 1. K is the number of groups or samples or populations. For example, in the baseball example, we have 9 separate populations. A population of people batting in first position, batting in second position, all the way through 9th position. The formula for the degrees of freedom for errors is n minus k, where k is still the number of groups, but n is the grand sample size. So it's the total of all the sample sizes of all your samples. In the baseball example, n was 270 because we had 9 samples, each containing 30 numbers. And then the total degrees of freedom is n minus 1. Now, we really don't need the total degrees of freedom, as you're going to see here in a moment, but the reason it's there is because sometimes you'll know 2 of these 3 degrees of freedom, but not the 3rd one. What you'll notice about this column is that it's additive. What does that mean? Well, that means that the first 2 degrees of freedom add to give the 3rd. From an algebra perspective, if you added k minus 1 and n minus k, the k's would cancel, and that would leave you with n minus 1. So all that means is that the 3 numbers in that column should make an addition problem. In fact, that's why this is total, because the bottom degrees of freedom is the sum of the first 2 degrees of freedom. And if you recall from the discussion about variability, we also have that additive nature in the SS column. That SS total was defined to be SS groups plus errors, SSG plus SSE. And again, the reason that additivity is important is we might have two of the three values in this column. We need these two, because we'll use them in just a moment. But let's say for a second that we have these two. Then we can find this missing one by simply subtracting, because the column is additive, meaning that the first two SS's add up to get the third one. But let's say for a moment that we get these columns populated, either because they're easy to calculate, like the degrees of freedom, or we're given values like the SS's. When you're checking for variability, you're comparing the variability created between groups with the variability created within groups. The problem is, if you go back and look at the formulas, the sums, this formula was originally adding 270 things, one for each element in all the data sets. Whereas this was the sum of adding 9 things, one for each different group or different population. So it's not a fair comparison to compare a sum of 9 things with the sum of 270 things. The way we fix that is we create what's called the mean sum of squares, MSG, so mean sum of squares for groups and mean sum of squares for errors. And the way we do that, well, it's right down here. The way we calculate the MS's is we just divide the SS by the corresponding degrees of freedom. So specifically, if we wanted to calculate this guy, we would take SSG and divide it by this. In fact, if you wanted to, you could just replace MSG. I can tell it to erase. You could just replace MSG with its formula, which is SSG for K minus 1. That's all this really says down here. And the same thing with MSE. You would just divide SSE off by its degrees of freedom in minus K. That's all this says down here. So whether you want to write the formulas inside the ANOVA table or write them below is really irrelevant, as long as you know that you calculate the MS's by dividing the SS by its degree of freedom. So you can summarize both by saying MS equals SS divided by degrees of freedom. You just do it in each row. You don't do it for the total. And the reason you don't do it for the total, I'm going to restore this back to what it was, is when you calculate the test statistic, that's the last thing that you do. The test statistic is simply the ratio of the MS's. I thought about writing the formula inside the table, but I'll just write it down here. The formula for the test statistic is MSG for MSE. But like I said, this table is really just a way to organize a lot of arithmetic. The first two columns are additive, so if you know two of the entries in the first or second column, you can calculate the third by adding or subtracting, depending on what's missing. But the truth is, we really only need these two. So if we're missing one, but we have the one on the bottom, we can do a subtraction column, figure out the missing one. Then to figure out the MS's, we just divide going right to left. SSG divided by K minus 1, SSE divided by N minus K. And then to find the F statistic, you pretty much just take this fraction. So let's say that what that would look like, shall we? Yeah. Go back. There we go. All right, so we're going to do this for the baseball problem that we did. So let's take a second just to go back and look at that. Operate. Here it is. I've zoomed in on just a part of the baseball, but I can zoom back out if I want to. Not that we really need everything. Oh, that's a little bit too far out. Not sure why it's showing page numbers. I don't want to see page numbers. There we go. All right. So if we're going to complete the ANOVA table for this baseball problem, we need to know a bunch of things. We need to know N, which is the grand sample size. That's 270. We need to know K, which is the number of samples. There were 9 samples. And we need to know all of our SS's. Well, let's go back to the ANOVA table and start filling in some things. All right, let's start with the k minus 1. The k represents the number of groups, number of samples representing the number of populations. And in this case, there were 9, one for each position in the batting order. Well, of course, 9 minus 1 is 8, so we can just put an 8 there. Next is our errors, our degrees of freedom for errors. N is the grand sample size, so that's 270. Minus the k. Remember, k was the number of groups. The number of groups was still 9. So if we subtract 270 minus 9, we get 261. And then the total degrees of freedom is just the grand sample size minus 1. But the grand sample size was 270. So 270 minus 1 is 269. And if you'll check real quick, this column is additive. If I add the first 2 degrees of freedom, it does give me the third one. So in any problem where you're given 2 or 3 degrees of freedom, you can figure out the third one. As far as the SSG, the SSE, and the SST, those all came directly from the calculations we did before. So let's go back and find those real quick. You're not going to see me switch to the spreadsheet. I'm looking at it right now. Our SSG was 118,956. 115,956. Thought that was going to be a black, but that's okay. Cool with red. SSE, the second one from our calculations, was 61,365.2. 61,365.2. 61,365.2. And I think I'll lose the 0.2 for now and just go to the nearest whole number. On your homework and quiz, I'll specify how to round each thing. And our SS total ideally is the sum of these. Now, it didn't come out to be exactly that before, and I'm attributing that to rounding issues, but say 180,000, 180,321, which is the sum of the 2 numbers above it. So again, if you know 2 of the 3 numbers in that column, you can either add or subtract to find the missing one, keeping in mind that the first 2 add up to the third. All right, now for the MSG and the MSC. I'm going to work them out down here and just write their results on top. Go to green. For the MSG, simply take the SSG and divide it by its degrees of freedom. Looks like 556. I don't like those letters, but I didn't choose them. I choose them. SSG, magnetic, S, divided by its degrees of freedom. So 115,956 divided by 8. That's just a calculator problem. The answer to that calculator problem is what's going on with my calculator, but I'm pretty sure that wasn't the answer. Divided by 8 equals. Now we'll take it to the nearest whole number, 14,495. There is our MSG racing. 14,495. Now, for the MSC, we do the same thing, we just do it in this row. So MSC, trace this down here. Trace this down here, please. Been one of those days, folks. I will not be defeated. I'll prevail. Bad text box placement on my behalf. All right, MSE is going to be SSE divided by its degrees of freedom. So 61,365 divided by 261 will be a much smaller number. 1,365 divided by 261 to the nearest whole number, 235. And so for our test statistic, which we'll do for our test statistic will just be the ratio of the MS's. Our test statistic is going to be F equals MSG for MSE. So we'll simply take 14,495 divided by 235, and round that. We'll take that one to 4 decimal places because we're about to compare it to an F value, 61.6809, 1.689. So it seems like a lot of calculations to do, but the truth is it was actually pretty straightforward because the formulas for the degrees of freedom were pretty straightforward. They were subtraction problems, so not a lot to look at. These values, more often than not, will actually be given to you, or at least 2 of them, in which case you can calculate the third. These 2 values were just obtained by doing division of the number to its left to the number 2 to its left. And then this value, which is found by dividing the previous 2. So what is this? This is our test statistic. If we were doing an analysis of variance test, which will be the next video, that would be our test statistic. All right, so hopefully you can now calculate the values in ANOVA table. They're really not that hard to do. You just have to know what your formulas are.